Okay, so we have a quick sentence to summarize that result, and that finishes up this problem. One of the other major ideas with the second derivative is that we can use the second derivative to find maxima and minima of a function, just like we can use the first derivative. So we have a second derivative test, and it's a little different than the first derivative. And not surprisingly, we're going to use concavity. So remember, the first derivative test says that we should locate any critical points, and then we should use the sign of the first derivative to the left and to the right of those critical points and infer from that information whether we have a max, min, or neither. So with the second derivative test, we can instead use at a critical point the concavity. So we would find any critical points, and then we would check the concavity. Concavity correlates with bending of the function. So you can see these two functions, f and g, are just little toy problems, and you can see their plots here. If you take their second derivatives, they look, they're just quadratic, so they have the form x squared. So I provided the functions above, but in any case, if you take the derivatives, you'll see that f has a positive second derivative, g has a negative second derivative. In other words, f is concave up on its entire domain, and g is concave down. So if you were to plug in the critical point x equals 2 into the second derivative of f, you would get a positive value. In other words, f is concave up there. And so you can see that what this implies is that if you are concave up at a critical point, then a minimum must occur. And similar statement is also true that at a critical point, if the function is concave down, that is to say the second derivative is negative, then you'll have a maxima there. So that's the second derivative test. And in practice, you can use either test. But if you find that concavity is 0 at a critical point, then the test is inconclusive. So that is a case that you might run into where if that happens, you need to fall back on the first derivative test. So just to summarize our results in this table, just like the first derivative test, the first step will always be to find any critical points of the function of interest, and then we'll plug those critical points into the second derivative and check the sign of the second derivative. If the second derivative is positive, that is to say if the function's concave up at that critical point, then we say that f has a relative minima or minimum. And similarly, if f double prime is negative at the critical point, then we say that f of x has a maxima at that critical point. Lastly, if the concavity or the second derivative is 0 at that critical point, then the test is inconclusive and it's unclear whether we have a max, min, or neither, and we need to do a little more work. We need to use the first derivative test. The good news is if that's the case, you've already found your critical points, and so you just need to check the sign of the first derivative for nearby values. So this example I want you to try on your own, and I'll fill that out. But as you can see, it's very similar to the example 2 that we just did. So I think it's more beneficial for you to try this one on your own. So go ahead and try it. Pause the video and try this now. All right, so let's see how you did. S is the sales of a product in millions. T is time in months since the product was introduced. We want to go through this part A asks us to look at each plot and determine where S is concave up and where S is concave down. So as you can see, you should have found that S is concave up for values of t from 0 to 20 and concave down for values of t from 20 to 35. Or to the end of our domain. So it doesn't really, it's unclear from this plot where the end of our domain is, so we'll just say 35. So how can you see that from the plot of S? Well, you could look at how the first derivative is changing. So go ahead and take some test points, or take your pencil or straight edge and take several tangent lines as you go, as you sweep from left to right. And so you can see from 0 to 20, the first derivative is increasing. The slope of those tangent lines are increasing. So this is this bending upwards. And what this means is that the second derivative is positive. And that is another way to say that S is concave up. And similarly, when you see that the function is bending downward, well, that means the first derivative is decreasing. So
that would be concave up.
So given a function, that's how you can identify concavity, is by paying attention to how the first derivative is increasing or decreasing, and that correlates with the concavity. So just kind of more intuitively, you can think about this as bending. So if you just imagine a really flexible stick, take a point, let's say at 25 in the function value, and extend your flexible stick out, And how would you have to bend that stick? You would have to bend it down here as we move forward in time. And so that means the first derivative would have to decrease. That means the function is concave down. So that's one way that you can think about this. That's a little more intuitive maybe. Looking at the second derivative, or the derivative plot, all we need to look for is where the first derivative is increasing to know where a function is concave up. So similarly, we can look at where the function's derivative is decreasing. So we're actually looking at the same property. So if we look at where the derivative is decreasing, that will tell us where the function's concave down. And similarly, if the derivative is neither increasing nor decreasing, the concavity. So that's a summary of those results there. So you can see if we look at about 20, the function is neither increasing nor decreasing. So the concavity is 0 there, but from 0 to 20, the first derivative is increasing. So we have concave up, and then similarly concave down from 20 to 30. So of course we get the same result, but the properties we're looking at on the derivative plot are different than the properties we're looking at on the original function plot. Lastly, and probably the easiest, is how would you interpret this if you were just given a second derivative plot? Well, concavity is precisely the sign of the second derivative. So we just need to look at the height here. So since the height is positive from 0 to 20, the second derivative is literally positive, then that means we're concave up by definition. Similarly, wherever the height is negative, we're concave down. So we can see exactly why that's the case if we have the second derivative. So that answers B, and as we discussed, or part A, I'm sorry, and for part B, we're asked about any points of inflection, and as we discussed, points of inflection are places where the concavity changes. So we can see that there's just one place here, and again, probably the easiest plot to use, since we have all three, is the second derivative plot. And so we see any place where the second derivative function slices through must be a place where the concavity changes, and that's because the sign of the second derivative must change there. So that's just by definition what it means to be a point of inflection. So lastly, the interpretation. I think it's probably easiest to use the original plot of the function s of t. And so you can think about it two ways. After 20 months, the rate of sales begins to decrease. The derivative starts to decrease. And that's another way to say it becomes concave down. So the concavity changed. And then alternatively, you could say after 20 months, sales are still increasing. So the derivative is still positive, but slower and slower. And that's another way to say that the second derivative is negative. So now let's look at this problem, and I'll do part A in some detail, and then I'll leave the remaining parts for you to try on your own, and I'll of course fill those in. So this question wants us to use the second derivative test to find any maxima or minima, and also to determine any points of inflection. So when you see determine any extrema, that's telling us to look for maxima or minima. So there's two separate problems for each part. So let's run through the second derivative test first and find any maxima or minima. And so the first step is always to find any critical points. So to find a critical point of h means to find any place, any values of t, where the derivative of h is 0. So we take the derivative and we get 4t minus 4. We set that equal to 0 and solve. And we have only one solution, which is t equals 1. So that's our critical point. So the next step is to check the concavity of the critical points. In this case, there's only one critical point, but I just wanted to remind you that there may be several critical points for any general function. So just be careful about that. Don't assume that there's just going to be one critical point. In any case, that just means to take the second derivative and plug in your critical point. So we take the derivative of the derivative. So we take h prime, and its derivative is just 4, because the derivative of 4t is 4. And the derivative of negative 4 is 0. So plugging in 1, well, h double prime is just 4. So anything we plug into it is 4. So that means that the second derivative at t equals 1 of h is 4, and that's a positive number. That means the concavity is positive, or that h is concave up at t equals 1. So when you're concave up at a critical point, you have a minimum at that point. So just a quick sentence to summarize our findings. So this question also asks us to find any points of inflection. So we have to remember the definition of a point of inflection is a place where the concavity changes. So we have the second derivative function, and if we didn't already have that, then we could find it. So if you're ever looking for points of inflection, find that second derivative. If you have a plot, that means of the original function, then that means plot the second derivative. But if you have an algebraic function like we do, then take the second derivative. So in any case, we have the second derivative, and we can plot that. You don't have to plot it, but I think that that will give you some insight into what the concavity is doing. So it's a constant function with a height of 4. And so the concavity is the sign of the second derivative. So what this means is that h is concave up everywhere. This is just another way of saying that the concavity never changes. So if the sign of the second derivative never changes, then there are no points of inflection. So just a quick sentence to summarize those results. So again, for the second derivative to check points of inflection, you're just looking to see if the concavity changes, and that another way to say that is to say, does the second derivative slice through the x-axis? Okay. So to give you a quick example, let's call this g double prime of some function g, and we'll just make some arbitrary labels. So you can see there are 3 places where the sign of g double prime changes at -1, 1, and 2, and so these would be 3 points of inflection of g. So that provides you with an example of a function whose second derivative clearly shows those points of inflection. So go ahead and try parts B and C right now. Pause the video and go through that same process and see what you can come up with, and I'll post those answers right now. So let's see how you did. Again, the first step will always be to take the first derivative and set that equal to 0, so to just find any critical points. And from there, you want to check the concavity of those critical points. So that's always going to be step 1, so that's what we did there. And we found 2 critical points at -1 and x equals 3. So plug those into the second derivative and check the sign. If you do that, you'll see that at -1, the second derivative is negative, and that is to say that f is concave down at that critical point. And so the interpretation there is that you have a maxima at that critical point. Similarly, we plug in 3 into the second derivative. We see that we get a positive value. We get 12. That's positive. And that means that we have a minima at that critical point. So that's the second derivative test for f. Next, we check to see if there are any points of inflection. So again, if we didn't have the second derivative already, we would find that, but fortunately we already did that work. The second derivative is 6x minus 6, and I would recommend plotting that. That will allow you to see really clearly that there is an x-intercept here. And it's not just that we have an x-intercept, but that the second derivative changes sign from positive to negative. So you can see here that is the case, and so set that equal to 0 to find that precise intercept, and that is at x equals 1. So we can see that the sign of the derivative changes from, the second derivative changed from negative to positive. That is to say f changes from concave down to concave up. So if that happens, we have a point of inflection at that point. So putting all of this together, we say that f has a point of inflection at x equals 1. Just to give you another example, let's take this function. We have the plot of the second derivative of a function h. So at -1, we see that the function slices through the x-axis, and so that we see that change of concavity. The second derivative changes from positive to negative. We also see another x-intercept at about 2, but the sign of the second derivative doesn't change. So at that point, there's no point of inflection. So just a couple of statements to summarize that. So it's not enough to just have an x-intercept of the second derivative. You need to slice through that x-axis. The sign of the second derivative needs to change, and that is just part of the definition of a point of inflection, that the concavity needs to change. So let's look at the last problem. And so the procedure is the same. So step 1 will be to find any critical points. So take the derivative. For this function, we get 20x cubed. We set it equal to 0, and there's only one solution, and that is when x equals 0. So that's our only critical point for w. Taking another derivative, we get w double prime, which is 60x squared. Plugging in our critical point, we see that that's 0. And so this is a case where the second derivative test is inconclusive. So the concavity is 0, and so that's not enough information to classify this critical point as a max or a min. When that is the case, well, that's okay. We'll just go back to the first derivative test. And so in practice, you can use either test you prefer. The second derivative test is a little bit quicker for most functions. So when it does work, it's quicker because you don't need to make a table, and derivatives are very quick to take. But the first derivative test will always work. So it's up to you to use whichever test you prefer, but you should definitely know both of them. All right, so using the first derivative test, we have our critical point at 0, and we take test points to the left and to the right. If you plot w prime, you see it's a cubic, and so any value of x less than 0 is negative, and any value of x greater than 0 is positive. This tells us that w is decreasing, flattens out, and increasing as we slice through that critical point. So that gives us a minima at x equals 0. Lastly, we determine if w has any points of inflection. We have that the second derivative is 60x squared, and again, I would recommend a plot. And so if you plot this, you can see that it's just a quadratic, and it's stretched with this scalar of 60. So it has a x-intercept at just one point at 0, and it's positive everywhere else. So in other words, the concavity never changes. So this is a case where it does, the second derivative does touch the x-axis, but it doesn't cut through. And so when that happens, we don't have a point of inflection. So there are no places where the second derivative slices through the x-axis in this case. So we have no points of inflection for w of x. So that concludes this lesson, and we'll see you on the next one.